Hello students, welcome to my YouTube channel, and today we are going to study about the spectral series of the hydrogen atom. In the previous video of this chapter atoms, we have studied about the Niels Bohr model, the postulates of the Bohr model, and we have seen the complete explanation about the Bose model. Now today we are going to study about the spectral series of the hydrogen atom. So let's start the video. Now one of the postulate of one of the Bose postulate states that when electron is making a transition from one energy state to another energy state, or basically from higher energy level to lower energy level, it emits the radiations, or it emits the energy in the form of the radiations, and the energy of these radiations, it will be equal to the difference of energy level of two states. So suppose these are the two different energy states of the atom. Let's see, this is your two different energy states, or two different orbits are there, and at the center we have this positively charged nucleus. The electrons are revolving around this positively charged nucleus. You can see it there. And when the electron is making a transition from one energy state to another energy state, let's see here, this is your positively charged nucleus, and electron is making a transition. Suppose here electron is there, and this electron is making a transition from one energy state to another energy state. This is your electron, and now it is making a transition from this energy state to lower energy state. The energy state of this, I am taking EI initial. Okay, initially the electron was in this orbit, and this orbit has fixed energy which is given by E initial. Now it is making a transition to lower energy state. Okay, and energy of this state I am taking E final. Okay, so when the electron is making a transition from higher energy level to lower energy level, it will emit the radiations in the form of photon. This, it will emit the energy. Okay, it will emit the energy in the form of the radiations. You can see it there. Okay, and energy emitted by this electron, it will be equal to, or it will be difference of energy of these two states. Basically the energy, or basically we can start from the beginning. When electron is making a transition, or simply we can say that when an electron makes a transition, makes a transition from higher energy level, higher energy level to lower energy level, to lower energy level, it emits energy in the form of radiations, in the form of radiation, and energy emitted, it will be given by, which is given by difference of these two energy states. Means energy emitted, it will be equal to E, then this energy emitted, it will be equal to difference of energy levels of two states. Initially the electron was revolving around the positively charged nucleus having the fixed energy E initial. Now it is making a transition to lower energy state, and its energy is suppose equal to E final. Then difference of these two energy states, it will be equal to E initial minus E final, and this much energy will be emitted when the electron is making the transition. Now the energy which is emitted in the form of radiation, it will be in the form of photon, and we know the energy carried by one photon, it is equal to h nu. So E can be written as h nu, it is equal to E initial minus E final. This is the difference of two energy states. Now we know the energy of the electron in nth energy state, it is given by E is equal to, the total value is negative, minus e to the power 4 into m divided by 8 into epsilon naught square into h square into n square, where n is your quantum number, n is giving you the number. So we can write down this formula. H nu is equal to, we can replace this value ei can be written as minus of e to the power 4 into m upon 8 into epsilon naught square into h square upon, or sorry, ni square, minus e final can be written as minus of e to the power 4 into m upon 8 into epsilon naught square into h square into n final square. Now after solving, this equation will become h nu equals to minus of e to the power 4 into m upon 8 into epsilon naught square h square into n initial square, minus minus plus, it will become e to the power 4 into m upon 8 into epsilon naught square h square into n final square. Now if we will rearrange this equation, then this equation will reduce to h nu equals to, just take the common terms out, e to the power 4. We can rearrange this equation like this also, e to the power 4 into m, first I am taking the positive term, upon 8 into epsilon naught square into h square into n final square, minus e to the power 4 into m upon 8 into epsilon naught square into h square into n initial square. Now take the common terms out from these two terms. So h nu can be written as h nu equals to e to the power 4 into m, this is common to both the terms, divided by 8 into epsilon naught square, it is also a constant term but is a common to both the terms, h square, upon, when you will take this term out, it will remain only 1 upon n final square, minus here in this term only n initial square will be there. So this is the equation now. Now suppose we are interested in finding the wavelength of the emitted radiations, then we have this formula: frequency into wavelength. Frequency into wavelength is equal to speed of light c. So from here we can write down wavelength or frequency is equal to c by lambda. This frequency we can replace here, so it will become h c upon lambda, it is equal to e to the power 4 into m upon 8 into epsilon naught square into h square into 1 upon n final square minus 1 upon n initial square. Now take the constant terms towards the right. H and C are the constant. So when you will take it towards the right side, it will become 1 upon lambda here only towards the left hand side, and e to the power 4 into m upon 8 epsilon naught square into h square. Now h into c, they are in the numerator towards the left hand side. When we will bring towards the right hand side, it will be in division, or it will be in denominator. So multiplied with h into c, and inside this bracket it is equal to n final square minus 1 upon n initial square. After solving this equation, 1 upon lambda, it is equal to e to the power 4 into m upon 8 into epsilon naught square, h square into h, it will become h cube into c. Inside this bracket we have 1 upon n final square minus 1 upon n initial square. Now this constant term, this term which is outside this bracket, e to the power 4 into m divided by 8 into epsilon naught square into h cube into c, it is a constant. This whole term is a constant. E is representing the charge on electron, that is 1.6 into 10 to the power minus 19 column to the power 4 we can write down, multiplied with mass of electron. Mass of electron is again a constant, 9.31 into 10 to the power minus 31 kg upon, just I'm leaving the units, I'm only putting the value in a size system. It is a constant, epsilon naught is also a constant, 8.854 into 10 to the power minus 12. You can check this value also, probably minus 11 or 12 is there, square into h cube. 6.63 into 10 to the power minus 34 cube and a speed of light 3 into 10 to the power 8 meter per second. When you will solve this equation, when you will just simplify this value, then the value will be 1.03 into 10 to the power minus or 10 to the power 7 meter inverse. Okay, towards the left it is 1 by lambda. Lambda has got the unit meters, so 1 by lambda it will be meter inverse. And towards the left and towards the right, both will be the same dimension, because n final and n initial, they are the numbers, and numbers are just unitless and dimensionless. So the unit will be meter inverse, and this constant, it is known as Redbug constant. Redbug constant. So now this equation will reduce to, now when we will replace this value e to the power 4 into m, it divided by 8 into epsilon naught square h cube into c by r, then this 1 upon lambda, it will be equal to r, where r is your Redbug constant, upon into 1 upon n final square minus 1 upon n initial square. So this formula we have established regarding the wavelength lambda and the energy states of the electron when the electron is making the transition. So from this equation we can analyze that when the electron is making a transition from one energy level to another energy level, just wait for a minute. When the electron is making a transition from one energy level to another energy level, basically it is emitting the radiations, and depending upon the energy state, from which energy state to which energy state it is making the transition, it will emit the radiations of particular frequency or wavelength. Okay, so different frequency and different wavelength we will obtain when the electron is making a transition from one particular energy state to another particular energy state. And basically due to this we will get a different series of the wavelength. Okay, we will basically get a spectrum here, and this spectrum is basically the arrangement of this spectrum according to their increasing wavelength of frequency. It is known as a spectral series, basically we will obtain. So our next discussion is the spectral series. So this is lambda here is basically wavelength of radiation that is emitted when the electron is making the transition. This lambda here, it is giving you the wavelength of photon, basically you can say wavelength of photon, or basically you can say radiation. And this n initial, ni, it is giving you the energy state, in which energy state it is. Energy state, initial energy state, energy state initial energy state of the electron. And n final, it is giving you the energy state final, means to which energy state the electron is making the transition, and they will be the number means 1 2 3 4 5, they will be in the form of the numbers, integers they will be. Now we can reduce this expression in terms of frequency also. Now just we have explained the relationship between wavelength and frequency. Wavelength into frequency is equal to speed of light, and from here we can find out the value of lambda. Then value of lambda, it will be equal to c by frequency. Okay, so this 1 by lambda, it is also known as wave number. Okay, wave number. Now if you will write down the value of lambda here, then lambda is equal to c by frequency, it is equal to r into 1 upon n final square minus 1 upon n initial square. After solving this equation, we can get the value of frequency. This value will become frequency upon the speed of light, it is equal to r into 1 upon n final square minus 1 upon n initial square. Okay, and from here we can get the value of frequency. Frequency is equal to r into c. C will be multiplied towards the right hand side, and it will be equal to 1 upon n final square minus 1 upon n initial square. So just we have calculated the wavelength and the frequency of the emitted radiations when the electron is making a transition from one energy state to another energy state. Now we will see the different spectral series due to the transition of the electron from one energy state to another energy state. Now we will see the different cases here. So this is the formula we have obtained. This formula we have obtained is a Redbug formula. 1 by lambda, it is equal to R into 1 upon, it is basically we have obtained n final square minus 1 upon n initial square. This is the formula we have obtained. Let me again check this formula. This is the formula we have obtained. You can see it there. Yeah, 1 upon n final square minus 1 upon n initial square. This formula is known as Redbug formula. Now we will see the different cases. First case I am going to explain. First case. Now suppose I am taking n initial. Okay, n initial or n final first I am taking, means electron is finally making a transition to the first energy state of the hydrogen, that is ground state, n final. And initially the electron was Ni, higher energy state we can take. Ni I am taking, it is equal to n, and this value may be 2, 3, 4, 5, 6, like this we can take. So here you can see you will get a spectrum here. When electron is making a transition from suppose 2 to 1, then you will get one spectrum. From 3 to 1, you will get one spectrum. Sorry, you will get one wavelength here. And 4 to 1, you will get one wavelength here. And when you will arrange this, wavelength in a particular fashion, you will get a spectrum here. You will get a series here. And this series is known as Lyman series. So now this equation will be modified as 1 upon lambda, 1 upon lambda, it is equal to R, and n finally means electron is making a transition to first energy state, means ground state. 1 upon n in final I am taking 1, so 1 is square minus 1 upon n initial. 1 initial I am taking n, suppose the value n, this value may change, means energy may be in the first excited state, n is equal to 2. It may be in third excited state, it may be in fourth excited state, fifth, sixth, or any excited state, and finally it is making a transition to its ground state. Then this, here you will get one series, and this series is known as Lyman series. So basically the name of this series you will get here is Lyman series. Lyman series, which lies in ultraviolet region. Ultraviolet region of electromagnetic region, and the series which you will obtain here, it will lie in the ultraviolet region, and this series is known as Lyman series. Now second case we are going to discuss. Now second case I am taking the electron is making a transition, and you need to choose from higher to lower, means finally electron is jumping to, suppose, first excited state. First excited state means n is equal to 2, and just choose a higher energy state from this. So initially electron may be higher than this, means 3, 4, 5, 6, 7, 8, like this. Means electron is making a transition from higher energy state n is equal to 3 to first excited state, that is n is equal to 2. It will emit the radiations and it will have some wavelength. Now when the electron is making a transition from n is equal to 4 to n is equal to 2, again it will emit the radiations and having certain wavelength, but wavelength will be different from the previous one, and you will get a pattern here. And the pattern, when you will arrange according to their wavelength, here you will get one series, and this series is known as Balmer series. It lies in the violet region, sorry, visible region. So this equation, the Redbug formula will be modified to 1 upon lambda, it is equal to R, is finally the electron is jumping to first excited state, that is n is equal to 2. So 2 square minus, I am taking this, initially it was in the nth excited state, that is n square, and the value of n will be either 3, 4, 5, 6, 7, 8 like this. Okay, and this series that we have obtained, it will lie in the visible region, and this series is known as Balmer series. Balmer series, which lies in visible region. And you know what is the wavelength of the visible region? The wavelength of visible region, it is equal to 400 nanometer to 700 nanometer. You can remember this, okay? Because sometimes when the value will be given, suppose it is in the range of this value, may suppose 600 nanometer, and they will ask you in which series it will fall, then definitely you can answer Balmer series. Okay, now moving to the next. Third, similarly we can explain about the rest series also. Now I'm taking this second excited state, means finally the electron is jumping to, suppose, second excited state. Excited state means n is equal to 3, and just initially the electron was in higher energy state to this one, means just you need to choose the value greater than this, means initially the electron was in this 4, 5th, 6th, 7, like this you can choose. Okay, and this value you can choose as n, then this formula, Redbug formula, will reduce to 1 upon lambda, it is equal to R into, similarly we can calculate the frequency also, 1 upon 3 square minus 1 upon n square, and this n will get its value from 4, 5, 6, 7, and similar explanation we can give. Okay, here also you will get a series that will be different from the previous one, and this series is known as Paschen series. Paschen series, and this series lies in, which lies in infrared region. Infrared region, region of electromagnetic spectrum. Okay, so this series is known as Balmer series, Paschen series. Next we have bracket. So similar explanation we can give, bracket series. Okay, so bracket series is your, finally the electron will jump into this energy state, means third excited state means n will be equal to 4, and just you need to choose the higher value, means initially the electron was in fourth excited state, okay, fifth excited state, sixth excited state, like this. And the formula of Redbug formula will change to 1 upon lambda, it will be equal to R into 1 upon n final is equal to 4, so 4 square minus 1 upon n initial, I am taking n square, where n initial is equal to n and its value is equal to 5, 6, 7, 8, 9, like this you can choose. Okay, and this series, bracket series, it also lies in, which lies in infrared region. Last three spectral series lies in infrared region, and the final is Fund series. The fifth is Fund series. Fund series, similar we can apply if n final is equal to your 5, and higher energy state we need to choose, it may be 6, 7, 8, 9, 10, like this, then you will get The formula, Redbug formula, 1 upon lambda, it is equal to R into 1 upon 5p square minus 1 upon n initial. N initial I am taking n square, where n initial is equal to n and its values are 6, 7, 8. Sorry, it will start from 6, 7. Yes, 6, 7, 8, 9, 10, like this. And this series also lies in infrared region. So this series is known as Pfund series. The Pfund series lies in infrared region of electromagnetic spectrum. Okay, so how we can remember? So we have 4 series. So initially you can remember like this: UVI. Okay, UVI you can represent. It will be simpler to remember you. I am giving you one technique here how to remember this. Just you can remember this formula: U, V, and I. UVI. Okay. So first U means ultraviolet. Ultraviolet. V means visible, and I means infrared. Infrared. First, first series, that is known as Lyman series. It will lie in ultraviolet. Then second is Balmer. It will lie in visible, and rest of the series they will lie in infrared. Balmer, after Balmer, Paschen, bracket, and this Pfund. You can remember like this, or you can develop your own technique to remember this. Okay, because it is very very important. Now we are going to discuss about the next, that is we will see the pictorial representation of this series. So our next topic is energy level diagram. We will see energy level diagram. So this energy level diagram is nothing but it is a diagram. It is a diagram in which it is a diagram in which the energies of the different stationary states of an atom are are represented are represented by by parallel horizontal lines drawn drawn according to some some suitable energy scale energy scale. So what is energy level diagram? It is nothing but it is a diagram in which we are simply representing the energy of different energy states or stationary states of an atom simply by drawing the parallel horizontal lines. And while drawing these parallel horizontal lines, we need to choose some scale, energy scale. And when we are drawing such type of diagram, which is representing the different energy state of the atom, then this diagram is known as energy level diagram. Now, such diagram are very helpful in understanding the concept of stationary states and the emission and absorption of various spectral lines. So, we have seen both the formulas. First formula we have seen this formula, energy in nth excited state or nth stationary state. It is given by En, it is equal to minus 13.6 divided by n square. where n is giving you the number, okay, integer 1, 2, 3, 4, like this you can choose. Now suppose I am choosing n is equal to 1. So when you are choosing n is equal to 1 for hydrogen atom, so n is equal to 1 is basically representing the ground state of the electron, ground state. And when the electron is in the ground state, its energy, suppose I am writing by E1, then E1 will be equal to, it is energy, it is in electron volt, so I am writing minus 13.6 divided by n is equal to 1 square, it will be equal to minus 13.6 electron volt. Similarly, when I am representing n is equal to 2, okay, so this is giving you the excited state. This is basically your first excited state. Suppose electron is in second energy state or second stationary state, then this state will be your first excited state. Okay, and energy of this first excited state, I'm writing E2, it will be equal to minus 13.6 divided by 2 square. 2 square is equal to 4. When you will solve this, you will get minus of 3.4 electron volt. Similarly, I'm writing n is equal to 3. This is your second excited state. All these are representing the excited state. Second excited state. And in this second excited state, we can calculate the energy by the formula, above formula, En is equal to minus 13.6 divided by n square. So E3, it will be equal to minus 13.6 divided by 2 divided by 3, n is equal to 3, so 3 square. So 13.6 divided by 9, it will come out to be 1.51 electron volt. Similarly, we can calculate for n is equal to 4, it will be your fourth excited state, and we can calculate the energy. It will be your third excited state. Third, let me just wait for a minute. This is your third excited state. This is your third excited state, and its energy E4, it will be equal to minus 13.6 divided by 4 square, means 13.6 divided by 16, it will come out to be minus 0.85 electron volt. In this way we can calculate the energy for n is equal to 5, okay, n is equal to 6, n is equal to 7, okay. In this way we can calculate all the energy. And similarly, when you will take the electron, suppose I am writing in this way, you can calculate for n is equal to 5, n is equal to 6. When you will take n is equal to infinity, then this state, it is known as ionized state. Okay, when you will remove the electron from the atom itself, then the atom will be ionized. Then this state is known as ionized state. Okay, ionized state. This state is known as ionized state. And here we can calculate the energy. En is equal to minus 13.6 divided by infinite square. Infinite is a very large quantity. When you will solve this, you will get 0 electron volt. Okay, so we have calculated the energy of all these states. Now we are representing this energy by parallel horizontal lines. By choosing some suitable scale, we will plot the graph. Okay, and this graph or this diagram we will obtain, it is basically energy level diagram. At the same time, we know this formula also. This formula we have just obtained wavelength also about the different series. When the electron is making a transition from one energy state to another state, it is emitting the energy in the form of the radiations, and its wavelength 1 upon lambda, it is equal to r into 1 upon n final square minus 1 upon n initial square. Okay, this formula we have obtained. Now we are going to plot the graph. We will plot the graph one by one. So for plotting the graph, What we are choosing, we are taking x-axis and y-axis. Like this we can choose. Let me choose this axis. Okay, yeah, we will try to finish within this line. This I'm taking first I'm taking n is equal to 1. This n is equal to 1, and when n is equal to 1, we know the energy is equal to uh, minus 13.6 electron volt. Here the energy will be minus 13.6 electron volt. Okay, along y-axis we are taking the total energy. Just wait for a minute. Along y-axis we are taking total energy in electron volt. Total energy of the electron. And next I'm taking n is equal to 2. N is equal to 2 I'm choosing. This is your n is equal to 2. Let me choose the blue line. And you to choose closer, n is equal to 2 I'm choosing. This is your n is equal to 2. Okay, then we need to choose n is equal to 3. N is equal to 3. Then we need to choose n is equal to 4. N is equal to 4. N is equal to 5. We need to choose n is equal to 5. N is equal to 6. N is equal to 6. In this way we can choose, and similarly we can take n is equal to infinity also. Okay, this in this way we can choose n is equal to infinity also. Similarly, when we will keep on moving, I'm representing by dotted line. Okay, now we will see one by one. N is equal to 1. Then we have the another term, n is equal to 2. Let me choose. This is your n is equal to 2. And energy when n is equal to 2, the energy is minus 3.4 electron volt. And n is equal to 3, it is minus 1.51 electron volt. N is equal to 3. Similarly, n is equal to 4. When n is equal to 4, the energy is minus 0.85 electron volt. N is equal to 5. N is equal to 5 minus 0.54. In this way you can calculate. Formula I've already given, minus 0.54. Then n is equal to 6. N is equal to 6. Our energy is minus 0.38 electron volt. And similarly, n is equal to infinity. When you will go to n is equal to infinity, the energy is your basically 0. Okay, so this is the energy. Basically you can plot this graph along the negative y-axis. I plotted along positive y-axis, no problem at all. Now we can represent the series also. Okay, series I'm going to represent here. Lyman series, Balmer series, everyone knows about this. Okay, so suppose one electron is making a transition. Let me choose this. Yeah, suppose electron is making a transition from n is equal to 2 to n is equal to 1. Choose the color dark. N is equal to 2, n is equal to 1. N is equal to 3 to n is equal to 1. All are jumping to first excited state, sorry, ground state. N is equal to 4 to n is equal to 1. In this way the electrons are jumping. N is equal to 5 to N is equal to 1. Okay, and similarly N is equal to 6 to N is equal to 1. Like this they are jumping. Then here we will get a series. The series is known as Lyman series. The next series is Balmer series. Now suppose electron is making a transition from N is equal to 3 to N is equal to 2. N is equal to 4, and similarly you can take N is equal to infinity also, no problem. N is equal to 4 to N is equal to 3. In this way the electron can make a transition. We can represent like this. Okay, this series also you can see here, and similarly this also you can choose 1, 2, 3, and similarly you can choose like this also. Electron is jumping from here and from here, like this. Many lines you can choose, no problem at all. And finally you can take other also. Okay. There in this type you will get the series. Just I have represented us by a simple line. So this series is known as Lyman series. This series is known as Lyman series. Lyman series. This is your Balmer. This is your Passion. This is your bracket. And this is your Fund. Here you can take more N is equal to 7, N is equal to 8 you can take. So this diagram is basically known as energy level diagram. So this is all about from the line spectrum of the hydrogen atom, and the spectral series also we have seen. Now we will see the de Broglie. The next topic is de Broglie explanation of the Bose model, Bose second postulate of quantization. We will see our next topic is, let me see this. The next topic of discussion here is de Broglie explanation. Basically D will be small. De Broglie explanation of Bose's second postulate of quantization. Bose's second postulate of quantization. So Bose's second postulate states that when an electron is revolving around the positively charged nucleus, its angular momentum is quantized. Basically its angular momentum is an integral multiple of h upon 2 pi. So we know from Bose's postulate, from Bose's second postulate, we know the angular momentum of the orbiting electron. What is angular momentum? The angular momentum, it is given by L, and it is equal to mass of electron, linear velocity v, and radius of the circular orbit around which it is revolving is r. Then mvr, it will be equal to integral multiple of h upon 2 pi. This is your Bose second postulate. Okay, where n is your integer, it may be 1, 2, 3, 4, like this. Now we will see this Bose second postulate. Sorry, Bose second postulate it is. Bose second postulate. Okay. Now this Bose second postulate we will see from the de Broglie. Okay. So let me draw this circular orbit around which the electron is revolving around positively charged nucleus. This is our circular orbit. So this is the circular orbit, and this is your positively charged nucleus. This is your positively charged nucleus, and the electron is revolving around this positively charged nucleus in orbit. This is our nucleus. Now, according to Bohr's theory, according to de Broglie, when a particle, because electron is a particle, so electron is associated with a wave. Means when it is revolving around this positively charged nucleus, basically it is forming a wave. Like this also we can choose. Okay. And in one orbit, two electrons are possible. One is moving in clockwise direction, other is moving in anti-clockwise direction. Any shape we can choose. So let me draw this graph also for you. Okay. Now electron is revolving like this. Okay. It is transmitting the energy in the form of a wave. Like this also you can see it there. Here also you can see. Let me draw the graph. For one electron, for other electron you can take like this also. A beautiful shape we have obtained here. You can see it there. So electron is revolving around this positively charged nucleus. Radius we can take. The radius of this orbit we can take r. R is the radius of this circular orbit. This is the radius of the circular orbit. Average radius we can take. This is the radius of the circular orbit. Radius of the circular orbit I am taking r, and mass of the electron is m. Now we know the distance between any two, you know, uh, or distance traveled by a wave in one oscillation. One complete path you can choose like this. You can see it there. I'm starting from here. I'm drawing with the black line like this. Here you can see. Okay, it is forming a full cycle here. Then the distance traveled during this wave, during this length, it will be equal to lambda. That is known as wavelength. Everybody know about this. Okay, this is your lambda wavelength. Now distance traveled by an electron in a circular orbit of radius Rn will be equal to its circumference. How much distance will be traveled by the electron in one complete revolution? We can easily calculate the distance. We can easily calculate the distance traveled by an electron in one complete revolution around positively charged nucleus. It will be equal to the circumference. Positively charged nucleus, charged nucleus, it will be equal to how much? It will be equal to the circumference. It will be equal to 2 pi into r. And within this length, suppose n number of waves are formed. Okay, and one wave occupy lambda distance. Now suppose, since, or if we can assume, if n number of waves, let me take these assumptions. When the electron is revolving around this positively charged nucleus, suppose n number of waves are formed. If n number of waves, okay, or n number of oscillation, basically we can say complete oscillation. If n number of waves, or you can say oscillations are produced, then we know in one oscillation the distance travel is lambda. Then what will be the total distance? The total distance will be equal to, waves are produced, then we can write down, then we can easily say that the total distance that will be traveled, it will be equal to n lambda, and this total length is basically equal to 2 pi into r. So 2 pi r, it will be equal to n lambda. Look, if n number of oscillations are produced when the electron is making, you know, the revolution, one complete revolution around this positively charged nucleus, then the total distance traveled in terms of wave, it will be equal to n lambda. but the actual length is equal to 2 pi r, that is the circumference of wave. So we can equate this equation, 2 pi r is equal to n lambda. Okay, now according to de Broglie, or according to de Broglie, we know a moving matter, because electron is a particle, or a moving particle is associated with a wave which wavelength is given by lambda is equal to h by p. Okay, so we can write down 2 pi r is equal to n, and lambda we can replace, lambda is equal to h by p. Okay, we know from de Broglie equation, we know a moving matter is associated with a wave that is known as matter wave, and the wavelength of this wave, or de Broglie wave, it is given by lambda is equal to h by p. So I have replaced lambda by h by p, and p is known as linear momentum. If mass of electron is m and it is moving with a linear velocity v, then its momentum will be equal to m into v, because linear momentum p, it is given by mv, mass into velocity, product of mass and velocity. Just rearrange this equation, bring mv towards the right and 2 pi towards the, sorry, mv towards the left and 2 pi towards the right. Then this will equal to mvr, and it will become n into h upon 2 pi. Okay, and from here we can calculate mvr is nothing but it is equal to angular momentum. So L is equal to n into h upon 2 pi. So if one wave is formed, then n we will take 1. If two waves are formed, two oscillations are 2, 3, so n is your integer, and this is nothing but it is Bohr's second postulate. Bohr's second postulate. So basically we have used the de Broglie explanation in order to just explain this Bohr's second postulate. Now we are moving to the limitations of Bohr's model. What are the limitations of Bohr's model? So next topic is limitations of limitations of Bohr's model. What are the limitations of Bohr's model? So quickly we will see what are the limitations of Bohr's model. The first limitation is that Bohr's model is applicable only for hydrogen or hydrogen-like atom. Means Bohr's model is applicable for hydrogen or hydrogen-like atom. Hydrogen-like atom is having one electron only. Atom having one electron, like having one electron. Okay. Number two, Bohr's model explains the wavelength and frequency of light emitted by hydrogen atom, but not their relative intensity. Okay. So Bohr's model, we can say, here you can see in the spectral series we have seen, Bohr's model explain about the wavelength and frequency of emitted radiations, but not their relative intensities. Their relative intensities. So it does not talk about the intensity of the different waves that we obtained here in the spectral series. The third limitation is it does not explain why only circular orbit is possible or chosen. We can take the elliptical orbit as we have seen in the Kepler's law of planetary motion. So the third limitation is why it does not explain why only circular orbit should be chosen. Orbit should be chosen when elliptical orbits are also possible, like we have seen in the planetary motion gravitation chapter, when elliptical orbits are also possible. This is your third limitation. And fourth, it does not explain the further splitting of the spectral series in magnetic field, means a splitting of the magnetic series. Sorry, spectral series. It does not explain further the splitting of spectral series. Splitting of a spectral series, as it is observed, a spectral series, okay, in a magnetic field, that is known as Zeeman effect. In magnetic field, that is known as Zeeman effect, and or in an electric field, or in an electric field, which is known as Stark effect. Okay, so these are the main four limitations of Bose model, and this is all about from this whole chapter. Hopefully you have understood.